So good morning, everyone. My name is Jiayi, and next to me is Chenxin. So we are from the University of Hong Kong. Our work is about the anti-cheat in video games. So in general terms, we design an invisibility cloak to prevent modern games from visual cheats. And before my colleague walks through the details, I'm going to introduce a little bit of our work's backgrounds. So as you may know, in recent years, the gaming industry market has grown rapidly. So the first-person shooters, or as known as the FPS games, are one of the largest genres in the industry with lots of popular games such as the Counter-Strike series, Valorant, and the CrossFire. However, as the market expands, cheating becomes the main problem in FPS games. So aimbot is one of the most prevalent and harmful form of cheats. So what is aimbot? So aimbot basically is assisting the cheaters to aim and shoot automatically, so it will sabotage the game experience. So we can further divide the aimbots into two categories, the memory access aimbots and the visual aimbots. So the memory access aimbots are the traditional ones. They access the position state information on the client stored in the memory to navigate the peripherals such as a mouse or a controller so that they can auto-aim and auto-shoot. So in this video, you can see that even if the cheater does not have the opponents inside, he or she still knows their exact locations. The visual aimbots, on the other hand, are newly emerging as the computer vision techniques are getting more and more mature. So instead of risking detection by accessing the memory, it accesses the image information on the screen directly. So it performs real-time object detection to plot the bounding box on the opponents and then navigate the peripherals to aim and shoot automatically. So importantly, this type of cheat is training, so you can easily find the cheat tutorials on the forums, or you can see that it's widespread on the YouTube, and Chinese news reported a rise because of this type of cheat has already cost millions of dollars in loss. So you might wonder why visual aimbot have become so popular in recent years. So it is because the industry now does not have functional solution against this type of cheat. So on this slide, it is a normal interaction process between the player and the game. The player obtains the information on the screen and then take actions. And as mentioned previously, the memory access aimbots extract the information from memory directly. So many existing anti-cheat systems such as Valve anti-cheat, Easy anti-cheat, and BattleEye can prevent the data extraction process or detect such a process afterwards. However, the visual aimbots operates independently of the game memory data, so just like the normal players, they only need to take action while looking at the screen information. So to achieve cheating, they only need to rely on the screen images or the videos. So this makes the existing anti-cheat dysfunctional. Besides, due to the matureness of object detection models, the visual aimbots are incredibly effective. Also, in modern FPS games, the primary game characters are human figures, making this cheat method is highly general. So a well-trained visual aimbot or visual model can be directly applied to other similar games without fine-tuning. Therefore, to address these challenges, we propose this invisibility cloak. So for the next part, I'd like to invite Chenxin to join us and share the design details in the following parts.
Yeah, thank you. So inspired by adversary attacks in computer vision, we propose a proactive defense framework for visual game cheating, namely Invisibility Cloak. So without our protection in the normal game stream, as shown in this figure, visual aimbots can easily detect the opponent. So the core idea is to add perturbations to the game screen, and we call these perturbations the cloaks. By adding our cloak, we can disable visual aimbots, preventing them from detecting any targets on the screen. So first of all, because we need to ensure the player's gaming experience, so it is critical to make our cloak invisible. And also, we cannot let players feel any lag in the visuals, so we designed the cloak deployment strategy to ensure the real-time performance. And we can't predict which visual model cheaters may use for their aimbots. Therefore, we employed various proxy models to ensure our method's transferability. And lastly, it is also important to make our cloak work well in different map and game scenarios. So we used a lot of game screenshot data for training to ensure the robustness. So without our protection in the traditional online game architecture, the unprotected display is vulnerable. Visual aimbots can easily detect characters on the screen. Before it truly displays on the screen, we add an extra step to the architecture, and we call it the cloak crafter, so which can generate two different types of cloak. With cloak's protection, the final secure display can effectively prevent visual aimbot cheating. So then let's talk about these two clocks generated by the cloak crafter. To ensure the effectiveness and maintain real-time performance, we need to pre-train a powerful clock offline. So when deploy this clock, it brings no overhead, and it can work in most cases. So we used a large dataset containing different maps and scenarios, along with various proxy models to generate this clock. And we call this clock the universal clock. And to ensure its robustness, developers can train multiple different universal clocks for different maps or game scenarios. And additionally, regular updates are necessary to prevent cheaters from adaptive attacks. However, we cannot guarantee the universal clock can cover all cases, so we may need to refine it online. But even if we constrain the queries, the refined clock generation speed is difficult to match the high refresh rates in modern FPS game. As a result, our strategy is to insert the refined clocks at intervals between frames. So by default, as shown in this figure, we deploy universal clock for all frames. And then we can replace some of this universal clock with refined clocks, and the interval is determined by us. So we can insert refined clock every 3 frames, or as shown in this figure, we insert one every other frame. So this strategy allows us to significantly reduce the effectiveness of visual aimbots while maintaining real-time performance. So how to generate these clocks? Here is the clock generation process. After we inputting the original game frame, our goal is to reduce the confidence score of visual aimbots in detecting characters in the screen as much as possible. So this is achieved by continuously updating our clock based on the loss function and gradient information. After several queries like the figure shows, we can effectively disable the visual aimbots. And also it is worth noting that because refined clock is processed online, so we need to constrain the query number to a very small value when the clock refinement is needed. And for technical details, please refer to our paper. Then let's talk about the evaluation part. Because of the time constraint, I will only introduce a few important ones here. So I will first introduce the performance of our approach compared to others. And then I will show the methods on defense effectiveness against adaptive attacks by cheaters. Finally, I will discuss whether our method achieves true invisibility and its performance in real-world scenarios. So to ensure and test our method robustness, the dataset contains 9 maps in Counter-Strike 2 and 7 maps in CrossFire. These different maps provide a diverse range of game scenarios. So for each map, we collected a large number of game screenshots. And here's part of our defensive performance evaluation results. It only shows the experiments on CF datasets. So to simulate real-world conditions where cheaters might use different visual aimbots, we test our method on 4 visual models. So ULV5N, ULV5S, V5M, and NanoDate plus M. Except the random noise, we also compare with some state-of-the-art adversary attack methods such as RACE, DAG, and TOG. So the first metric is defense success rate, and the results show that our defense can achieve 100% defense success rate on all these 4 visual models. And the frames per second here is now the refresh rates in modern FPS game. It directly demonstrates the efficiency of our approach in generating refined clock. So it is the refined clock generation speed. And although some other methods can achieve high defense success rates, as shown in the previous slide, only our clock crafter can still maintain a high FPS. So finally, the query number also represents the speed of generating refined clocks. A low query number means that it spends less time on the refinement. So our very low query number further demonstrates the efficiency of our method. To test whether our defense remains effective, after cheaters may obtain the universal clock and fine-tune their models based on the clock, we conduct adaptive defense evaluation. However, the results show that adversary training with universal clock reduces the defense success rate by less than 20% on the CS2 dataset, and indicate that our clock defense remains highly effective even against adaptive attacks. To verify whether our clock is truly invisible, we conducted a user study. So in our survey, we designed several questions. For example, here, we asked participants to distinguish between frames, game frames with the clock added and the original game frame. The results show that the accuracy is lower than random guessing, proving the indistinguishability of our clock. Additionally, we verified that the natural list of the screenshots with the clock added is almost the same as the original game screenshots. Finally, we asked participants at what level of aimbot accuracy they would consider using it. So the results show that 90% of them would not accept an aimbot accuracy below 70% because it would significantly affect their user experience. So this indicates that if we can significantly reduce the performance of aimbots, the goal of our defense will be achieved. As a result, we test our clock in real-world scenarios to check how much it can reduce the performance of visual aimbots. So here is the demo of real game screen in the CS2 training ground. The bottom left corner shows the visual aimbot detecting all enemies on an unprotected game screen. While in the top left corner, you can see that the visual aimbot detection results after adding our cloak. So it demonstrates that our cloak completely disables the visual aimbots. Yeah, so we test our clock in real matches, and in these 2 30-minute game seasons, the visual aimbot could only successfully auto-aim a few times, from 1,000 times reduced to several times. So this indicates that our method achieved an almost 100% defense success rate. So for more demos and examples of the generated clock can be found on this website. You may scan the QR code to visit our website. Please feel free to check it out. Thank you for your attention, and we are very happy to answer your questions.
Great.